Hi, I'm Nathan, and this is my autocomplete project. So, the part of the binary search autocomplete class I'm most proud of programming is being able to sort a list with one call to collection sort in the add all method of the binary search. And I enjoyed being able to simplify that step that seemed complex, even though it really wasn't. And just being able to do it all in one line was pretty cool. For the ternary search tree autocomplete class, I'm most proud of programming the add all method as well, since in my implementation I used a for each loop to iterate through all the terms in the terms array I created to work with the overall root of the method, and I simplified adding them in to the data structure using the put method, and that put method was really difficult because we had to adapt off of that other code, and I'm really proud that I got it working because it was so confusing. For the worst case runtime of the add all method for sequential search, I said it was theta n because elements dot add all terms method it iterates through every element only once, so it should just be theta n. For binary search, it should be theta n log n because it uses tim sort within collection sort, so know that it's this runtime. Also, theta n log n is a common runtime for tree sorts. When you're adding with tree sorts. Ternary search tree is theta n because you can directly insert each term letter by letter. We're not counting the letters in that, but yeah. Tree set, we're just assuming as adding the letter part is constant time. Tree set autocomplete is theta n log n because adding to the tree set is a log n operation because it's kind of like divide and conquer, or the way that you go through the tree, and that is done for all n elements. The worst case runtime for the all matches method for sequential search is theta n because you have to search through each word to find ones that have the prefix that's mentioned, and you always have to do that for every word. So there's no prefix magic you can do. You have to go through every single word. For binary search, it's on log n because you have to do a binary search to find where the prefix starts in the tree and then go through all the instances where that prefix is used in that section. For ternary search tree is theta n because all matches will be at the correct prefix at the first time, which is found letter by letter. So getting to that prefix would run in constant time, but then actually writing all of those words into a result list would be that theta n that you see because all the elements have to be added in. And then for tree set autocomplete, it's theta n because you can find the tail set in constant time, just like in ternary search tree. Then you add all the terms in that scope which have the correct prefix, which reduces runtime to theta or on. Well, I guess it's not constant time, but whatever. So when comparing runtimes across different implementations, I expected ternary search tree to be the fastest compared to the other algorithms because it is best for inserting terms in constant time and getting to a prefix in that same constant time. And I expected binary search to be the slowest because you have to add terms using a sort, then accessing all the matches is still an expensive process in the end. So yeah, the charts, what they ended up showing is that sequential search had the best performance for add all, a worse performance for all matches given our specs for the way that we did our trials up here. Binary search had very bad performance for add all, great performance comparatively for all matches. Ternary search tree had bad performance for add all, great performance for all matches comparatively again, and same goes for tree set autocomplete. Pardon me for not having the label here. It will be there, never mind. And the reason why I think that this happened is because our max size is 20,000, so when you try to add all of those in, it makes this add all method very labor intensive for these different classes, however, or data types. However, for sequential search, because it doesn't have to sort every time you add something in, it doesn't have that bad of a runtime for add all, whereas it does have a worse runtime for all matches. Yeah. So were there any disagreements between the runtimes I hypothesized in the asymptotic analysis and the runtimes I observed in my experimental graphs? I'd say that the hypothesis I made on the last slide was wrong. The one specifically about how ternary search should be fastest compared to binary search. But I also believe that my runtime that I hypothesized for binary search, specifically for all matches, is wrong because I thought that in that one it should be n log n, since it has to actually sort through the binary tree to find the n, n being all of those elements with a certain prefix. But what I ended up finding out is it has the same performance as some of the other classes, or at least relatively similar performance as some of the other classes. So I think finding that prefix is a log n sort of thing, but then we can say it's theta log n plus n, which ends up actually just making it theta n. So it's not any type of linearitmic log runtime. It's just linear. That's what I think I hypothesized incorrectly. Um, so what I wanted to mention was this experiment, the way that it was laid out, it goes to show how runtime experiment variables affect the way that the data structures perform. Ours were very adding heavy, so the add all methods were pretty loaded or overload, not even overloaded, but just normally loaded during the time we were running these experiments. And what I noticed is the all matches one still performed great. So what that shows is even if there's 20,000 terms being added, if you can reduce to a certain prefix and you only get 10 terms left, it's a lot easier to add in 10 terms. So then it comes down to this question of how can we get to that prefix in the fastest time? And ternary search tree and tree set autocomplete are great examples of that. But binary search actually did a great job with those prefixes too in this example.